Good afternoon, everyone. So today we have organized in association with the Department of Studies in Physics, Mysuru, top title Laboratories in the Sky by Dr. B.S. Shylaja. ನಿಮಗೆಲ್ಲ ಗೊತ್ತಿರ್ಬೋದು ಡಾಕ್ಟರ್ ಬಿ ಎಸ್ ಶೈಲಜಾ ಅವರು ಬೆಂಗಳೂರು ಪ್ಲಾನೆಟೇರಿಯಂ ಜವಾಹರ್ಲಾಲ್ ನೆಹರು ತಾರಾಲಯದ ಹಿಂದಿನ ನಿರ್ದೇಶಕರು ಮತ್ತೆ ಹಿಸ್ಟ್ರಿ ಆಫ್ ಆಸ್ಟ್ರೋನಮಿ ಮೇಲೆ ತುಂಬ ಎಕ್ಸ್ಟೆನ್ಸಿವ್ ಆಗಿ ವರ್ಕ್ ಮಾಡ್ತಾ ಇದ್ದಾರೆ and also not leaving her core area that is astronomy and astrophysics and she's doing any number of things in astronomy. So I welcome Dr. Shylaja to this invitation. Welcome.
Okay. So good morning, good afternoon. You have heard me before, I think, right? Many of you have heard me before. So in the last talk, my obvious observation was that none of you opened your mouth. You did not ask a single question. I hope you will ask at least a few questions today. And this, I'm sure, is going to be of interest to you. And in case you are interested in continuing the ideas that I am providing here, you are welcome to communicate to me, and then we can do a small project or some such thing. That's the idea of this workshop, this particular talk. So when I say laboratories in the sky, the word laboratory will immediately tell you about the physics lab you are doing. So if you want to study some particular property of anything, you take a sample or the object itself to your laboratory and do the physical analysis there and take it to the chemistry lab and do the chemistry part there and so on. And therefore you get a complete picture of the object. But can you do that with the stars? You cannot. So how do we proceed? We make a good number of theories. I'm going to start with one theory which all of you are familiar with, and then it will be only a story unless you lace it with some evidence. So how do we get the evidence? How do we prove what we are telling in the theory is correct? So this is what I am trying to convey, and let us see how successful I will be. So the big questions are, how do stars live? First of all, we assume that they live. Okay, that means they are born and they are going to die. So how all these things happen and what is the process behind that? You already know physics, physics to understand these phenomena. Maybe some of you have studied also in the course you are doing. But then comes the question of how people thought about it, and you all have heard about the famous work by Hans Bethe, who introduced fusion as a fusion means nuclear fusion as a source of energy for the stars. And you know the meaning of fusion, so I have put it in very brief sentences here. So the particles being fused have the same electrostatic charge, and therefore they repel very strongly. This is the basic idea. Then somehow you have to make them fuse together. So how do you do this? You increase the temperature. That means you compress the gas so that the fusion can begin. The pressure and the temperature both you are going to raise very high. So this is all theory. So this is the theoretical work which said that fusion is possible. You know the physics behind it quite thoroughly in your physics lessons. So you have here the formation of the new elements as a consequence of the fusion reactions. So here you have the electromagnetic radiation which is coming out because of the fusion reaction. So in the physics lesson, you were only concerned about this part, namely the new nucleus that is being formed. But here we have to be worrying about the electromagnetic radiation that is coming out, but because that is the one that gives us the information. And you have So you all know that you start with 4 protons and then they will fuse to form helium and 2 gamma rays and 2 positrons and 2 neutrinos. These are also byproducts that are coming out of this reaction. So in the process, we have to be catching these gamma rays. What is this gamma ray which is coming out as a photon? And that is the one which is going to tell us whether what we are telling as the theory is correct or not. So that's where it begins. Okay, then you have many processes, so 2 protons fuse. What is this called? This entire scheme of operation. What is this called in your physics classes? At least now you have to open your mouth. You can't keep quiet. What is this called? What is this reaction called? This is PP reaction. Have you heard the name? So this is the PP reaction. So far I have been talking only about the PP reaction, and what Hans Bethe did was not the PP reaction. He did work on another thing. What is that called? You know the name, but you are not able to tell me. Okay. So let us continue. So this is the equation that is given to you in your physics textbook. So what I explained to you is all this. And when I tell this to high school students, it's very difficult to make them understand this repulsive force and all that. So we create a story. Okay. So okay, these are these different steps. I don't think you needed all these things. So let me jump. So this is one diagram which is presented to you, and I don't think your textbooks will carry such colorful ones, but it will carry that only that equation. Okay, so this is the story I am going to tell you. There are 2 protons here. Now you will not forget what is a PP reaction. So these are the 2 protons which are being repulsive, and then the electrostatic force is the one sitting in the center and preventing them from fighting. Okay. Then what happens? A magician comes. He is called a quantum magician, and he creates a tunnel into which these 2 can go. You know the quantum tunneling. You are physics students. That is what I am telling. And then inside they don't fight anymore. And this is the strong force. This is the strong force you have heard. And because of this union, you get what? Why did the strong force create this? Make them unite, so that you get the helium and all the other associated things. So I use these pictures to tell about this to the school kids. Okay, I am showing this to you also, so that you can make the dry equation into a very colorful thing. That's the only idea. Okay, now let us leave this picture behind and proceed. So it is the energy production which is responsible for the luminosity of a star. That is the gist of what I told you just now. And then you have the difference is exactly accounted by the, you know this also. In the process of 4 protons combining and producing 1 helium atom, something is lost, and that is the one that comes out as energy, and that is expressed by the famous equation. What is that? What is that equation? There. Okay, so you have all this in theory in your physics classroom. Okay, then okay, this is the same thing explained. You know this, so you have the difference as 0.048 into 10 to the power of minus 27 kg, which according to E is equal to mc squared will give you so many joules. And that's the same number you get from the other equation also. Okay, now when the temperature is very low, it is this PP cycle which is used for converting hydrogen to helium. PP is getting converted. 6 protons turn into helium nucleus, and that is the equation. Now, if the temperature, this temperature requirement is 8 million K, and that is why you cannot do this experiment in the lab anywhere here. That is the lowest possible thing in the case of stars. Okay. Then let's say you have a medium temperature fuel. Then you have what is called as the CNO cycle. CNO, I suppose you know what is CNO cycle. So that was the work done by Hans Bethe. He tried to explain the energy production by that mechanism. So you have, in the case of temperature from 20 million K onwards, CNO cycle will dominate. Okay. And you can have, what is the CNO cycle? Okay, that is briefly explained here. You have to start with a 12C, which absorbs a proton and it becomes N13. Then it sheds out a positron to become 13C, and then it absorbs another to get converted to nitrogen. Then another proton to turn to 15 oxygen. Then it sheds out another positron, and then you have another proton, and then you have the 4 helium coming out, and your 12C is back. This is the CNO cycle. So you start with the C12, absorb 4 protons, and then get a helium. It's the same process of 4 protons combining to form helium, but then the process is completely different. The temperature requirement is different because of that, the energy output also you expect it to be different. Okay, so you have high temperature fuel where CNO. Then you have still higher temperature, what is called as a triple alpha reaction. I don't know whether you have studied this, where 3 of the 12C combined and you have helium again, and so that is at 100 million K. So which is the type of reaction that is prevalent in the star is decided by the temperature at the core, because all this happens at the core, not at the surface of the star. Surface of the star, as you know, has a lower temperature, 5700 in the case of the sun. Okay, so very disgustingly high temperature. So you have so many things. So up to about iron. Okay, so you have all the other processes taking place here, and as a consequence, you have many other elements formed: oxygen, nitrogen, magnesium, silica, all kinds of things you see in the periodic table, and up to iron. Okay, and the temperature required for that is 600 million Kelvin. This is all from theory. Okay, that is carbon burning will take place after 600. So as you see, as the temperature before increases, you have various types of different reactions, nuclear reactions taking place. Well, where do the rest of the elements come from? Well, the periodic table does not stop. Right? Okay, so you have so many of them. Where do all these things come from? So you have it up to 92. Okay. The ones beyond that will not be discussed now. You have a separate discussion for that. But right now, let us stop at 92. So these are all produced at extremely high temperatures and at extremely high pressures and densities, which are possible only at supernova events. So supernova is the death of the star. It's a thing that is happening at the final stage of very massive stars. That's a separate thing. Now what I'm trying to say is that this is the theory. This is how the stars are producing the energy, and they survive by this mechanism. So okay, this is the same thing. We said that we are all star stuff. That is because everything other than hydrogen was nucleosynthesized in the core of the stars and exploding stars. So everything that you see, every molecule or every atom that you see around here was contributed by some star or the other. It is in that sense that Carl Sagan said we are all star stuff. Okay. So you can imagine how many millions of stars would have contributed for one drop of blood in my body. So many millions of them have contributed to that. Okay, so how are these stars created? Now that we have talked about how it lives, now we have to talk about how were they born. So you need to look for some examples in the sky and say, okay, see, we have seen something happening here, and this is how the stars are born. Because you can't go and inspect what is happening there. It's humanly impossible for us to do that kind of an experiment here. So you have a low mass cloud where gravity and pressure both are operating, and then you see that the pressure wins and the cloud keeps on expanding. On the other hand, if gravity wins, then the cloud contracts and you have the star formed. But dust is not enough. You need many other things also. One is the motion of the particles and the magnetic field and the rotation. It needs to be rotating slowly. It can't be sitting quiet. And so here you have an example. It's a star forming region in a different galaxy. See, from far away we are able to see an overview of the star forming region. This is a galaxy which is quite far away. So it is believed that all the stars are formed like this, and if it is forming in our vicinity, we will not be able to see it because the dimensions are so large that it envelops maybe a huge area of the sky, and we will not be able to even realize it. They don't emit light. No light is being emitted because no energy is being produced by these gases. Okay. Then you have the shock waves traveling through nebula. They can make them coalesce, and then gravity takes over, and so on. So these are all theories. Okay, so you have the molecular clouds becoming sites of new star formation. So you have this, which is condensing. Then you have these potential, kinetic, and angular conservation of angular momentum. All these things working together to ultimately produce a ball of gas, which you can call as a protostar. Okay, so to conserve energy, the cloud gets hotter and hotter, and then for conserving the angular momentum, it has to rotate faster and faster. So all these things should be happening simultaneously for a star to be formed. Okay, I did not include the magnetic field part here, so you have a star being formed there. So a big cloud has a high potential energy, low kinetic energy, and low spin speed. But when it becomes smaller, its potential energy reduces, the kinetic energy increases, and the spin speed also increases. And that is how the star is formed. So you need to see in a cloud a star which is taking shape. So how do you identify that? So the disk will be emitting owing to its temperature like a black body, but not at 5,000 or something. It must be much cooler, and you should be able to sense it. Your eye cannot sense it, but the infrared detectors can sense it. That is how the infrared astronomy becomes very important, and the recent telescope, James Webb Telescope, is looking at all the such star forming regions with its infrared eye so that it can pinpoint and say where the star is forming. Okay. So afterwards the rotation takes over, and then the material, 99% of it goes into the star, but the remaining will spread out as a disk. Again, there it is the conservation of angular momentum which becomes important. Okay. So I'm trying to tell you the physics principles that are involved here because you are all physics students. It is not magic, it is not a story. It is physics that has gone into every one of these things. Okay, so now this is the solar system. Okay, no, okay, I missed one slide there. No problem. You know that. So when it is the hotter the gas, mm, gravity takes over, and then finally, when there is a collision, the gravity will have to take over. That means the collisions can make the individual molecules get kicked away. But if gravity is strong, then they will all coalesce into formation of the sun. If that has to happen, the pressure has to be more, and the velocities of the individual particles will have to be also taken into consideration. Okay, when it is hot enough, this is the way it happens, and then you have the star form. That means if you look at a young stellar object, a star which is just born, there will be a cocoon around it, some kind of a dusty cloud. So even if you are not able to see the star, but if you are able to see the cocoon in your infrared eyes, you can make out that there is a star formation. There is a star formation activity here, and eventually all that cloud will move away and the star becomes visible. So this is what James Webb Telescope is going to look at, these kinds of regions. Okay, so this is the same process which I explained, and the youth is headstrong. All of you know that. I don't have to explain it. You are experiencing this. Okay. So when the temperature is not hot enough, the outside infrared radiation emitting gases will start interacting. Okay. And that is where the planet formation can take place. So all these planets are formed in the disk outside. And if you see some kind of a disk structure around a star, it means that planet formation also is very active there. And after these missions called Kepler and recent SIPs and other things, we have found that almost every star has a planetary system around it. It's only that we were not able to see it all these years. So now the total number of extrasolar planets which have been discovered has crossed 5,000. So every second star in the sky, you can say that it has a planetary system, which may resemble our sun, our solar system, or it may look completely different. So that is the infrared radiation. And okay, now, okay, so this is the effect of the magnetic field and so on. So this jet is another symbol. So if you see some kind of a jet action which you can detect with the radio telescopes or even the infrared telescope, that will tell you that the star planet formation and the disk formation is active. So we have to be looking at the star not only with the visible telescopes but with infrared as well as the other radiations. Okay. Now you remember that we were doing all this infrared radiation, etc. We have been doing it only in the last 3-4 decades. Before that, our infrared observation was limited to balloons. People would take instruments in the balloon, and in the 4 or 5 minutes, which is when it is hanging up in the sky, it will send some data, and that's the only information you had. So before that only all this theory had been formed. So how did they do it? It's all with basic physics. So you have some kind of a structure which will resemble the form of the exhaust coming out of there, and you have to look for such examples. So there is one example, I think here. This is the example. You can very clearly make out that there is some kind of a axis here, and then that is the jet in which it is ejected. So if they are able to get these kinds of images, immediately you can say that this is a newly formed star. So okay, this is it's red. We said this rectangle. But then all of you can see that it is not looking red. It's looking yellow. That is because of the dust which is surrounding it, and the dust is doing some mischief so that it looks of a different color. So you should know that you should correct the color for this kind of dust action also. Extinction by the dust. Okay. Oh, I don't know whether you know this diagram. I will skip this because I don't know. Have you seen this kind of a diagram before anywhere? This is called the HR diagram, which is a graph actually of, I think we'll come to that. That is the position of the sun, which is in its middle age. So when we say middle age or the main sequence, we mean that it is using hydrogen to produce helium, and therefore it is shining. That's the meaning conveyed. Now immediately the question arises is, what if there is a star and if it is not on the main sequence, how else can we see it? Okay? So that is the next process. So now comes the age. So how does the star evolve? It is something like telling a baby and adulthood. And what I have told till now is the adulthood. Now it is the old age. And the old age is very short. The baby or the infancy is very short. But it is the middle age which we consider as the age of the star, which can be 10 billion years, 1 million years, depending on its mass. Okay. So now let us consider that of a solar mass star, that is something like our own sun. During this phase, it was on this zero plus. Okay, I should have shown the graph first, but it's okay. I think you can understand the text that is written there. So it is radiating heat and starts swelling slightly as it ages. So on this graph, it moves slightly towards the right. That's the meaning. So what is this graph? We will understand it. So that is the position, and so it is moving away from the main sequence. Main sequence is that band where most of the stars are located on the graph. I will come to the graph. I think it will be there somewhere. So this is a misconception. People think that as the star becomes old, the sun, for example, it will become blue. It will become larger and blue. That is not true. No, it will not become blue. It will become red. And what is the meaning of becoming blue and becoming red? Blue means the temperature should increase. Red means the temperature should decrease. That is the meaning that is conveyed, because all of you know from black body formula that red corresponds to a high temperature, lower temperature, and blue corresponds with higher temperature. So that is wrong. Okay, sequence. Okay. Okay. Here is the graph. This is the graph I was telling. So this is the graph I was. The x-axis is the temperature. Please note that the temperature is increasing this way, and the luminosity is increasing. So if you plot this, almost all the stars in the sky will fall into that band, and that is called the main sequence. So all the previous pictures that I explained was with reference to this graph. The axes were not marked. So when I said it is moving right, it is moving right, left, etc., I meant increasing temperature, decreasing temperature, increasing luminosity, etc. Now, on this, the same graph, whatever we discussed earlier, how will it look? Now, look, what's the star which is growing here, and simultaneously watch its position on the graph. So, protostar, main sequence, and old star. So when it is a protostar, you don't find its position on this graph at all because the temperature is too low. It's on the other side. It is not fitting into this. When it is on the main sequence, it sits in that region of the band that is shown as the main sequence. and when it becomes old, it moves away from the main sequence. So instead of explaining like this, we are going to explain it like this in the graph. That's the meaning. So that is the graph. So it was at a very low temperature, it increased the temperature, came onto the main sequence, evolved away from the main sequence and disappeared from the graph. That's the meaning. So what was explained here as the animation is explained by the graph. So as students of physics, even if I don't show this animation, you should be able to understand that by looking at the graph. Okay. Now, they don't move up and down the main sequence, but they move across it. That's the meaning. Okay. This is for the sun-like star. How does it gain mass? Because star is a huge body, let's say the sun. So it keeps attracting all comets and other things. So you expect that it will be gaining mass. But on the contrary, it will be losing mass. So how does it happen? They are so incredibly massive, they would trap any gas dust in the vicinity. Then why don't they suck up all the planets? You know the answer for that. But they don't do that. So it's gravity which is taking it in, but in fact they are losing mass. That is because of what is called as the stellar wind. So you have a series of, that means it keeps throwing out matter by some processes that are happening in the outer regions. So it loses mass in the process. So when the sun, sun is expected to live for 10 billion years. It has already spent about 4.5 billion years. After another 5.5 billion years, what is left at the center of the sun will be only half of its mass. Then what happens to the other half? The entire other half is not converted to energy. Only 10% of its mass is converted to energy by the proton-proton reaction. The rest of the 3 or 4% mass, 70% mass, is thrown out as stellar wind. So you keep hearing about what are called coronal mass ejections because of so many things. See, they interfere with our satellite system, artificial satellites, and they create colorful lights in the polar regions. You would have seen interesting photographs of them. All that is the mass emitted by the sun. It looks small compared to that, but over millions and billions of years, the sun loses half of its mass almost. So it keeps losing mass, and therefore, ultimately, what you have at the time of death of the star is only a small percent of its original mass. So it can be 0.5 solar masses, or it can be, in case of a massive star, 2 solar masses, something like that. This is nice theory, but then how do you prove that such stars exist? There are stars which are smaller than the sun, which look more luminous, but then they're very compact. Then there you have to understand about phenomena which was first proposed by Chandrasekhar. What is that? Yes, Chandrasekhar. You would have studied that related to electrons. Electrons. You have studied it, I think. Electron degeneracy. You have heard the word degeneracy? I think you are introduced to that. It is the degeneracy pressure which takes over and therefore holds the matter together because of that pressure, but there is no energy production. That kind of an object is called a white dwarf, and that limit of mass is called the Chandrasekhar mass limit. Okay. Whatever material was there was thrown out. Okay. Not towards it. Okay. A large star. Now I told you about the sun-like star. A larger star, which is 10 times more massive than the sun, let's say, can lose 60% of its mass. It can lose 60% almost. So a 10 solar mass star ultimately can be only a 2 solar mass star or 3 solar mass star. it is more than the Chandrasekhar limit. Chandrasekhar limit is 1.4 solar mass. I am using the word solar mass equivalent to a kg. Instead of telling 1.4 kg, I am telling 1.4 solar masses. The one solar mass is 10 to the power of 30 kg. 2 into 10 to the power of 30 kg. Every time I don't have to say 2 into 10 to the power of 30 kg. So I use the word solar mass for that. Okay. Then how does that evolve? Now this is a comparison of these two situations. This is based on the theory. So here you have a star like the sun and another star which is more massive than the sun. So let us see what happens. Both of them start as protostars and they pass through the main sequence, and let's see what happens now. A less mass star, the longer it takes to evolve. So just observe what is happening. So this is obviously, you can very easily remember now that the less mass star survives longer than a higher mass star. The higher mass star evolves faster, finishes its main sequence, means adult phase, very fast and dies, whereas the less massive one is still surviving on the main sequence. So this is a situation similar to a rich man and a poor man. Rich man spends a lot of money, so he spends all his money fast. And the poor man, instead of going to Delhi by flight, he decides to go by train, and so saves a lot of energy, and therefore he will survive longer. He will have the money for a longer time. Well, what happens later on is you have to stop at the analogy here only. Don't extend it beyond this. Okay. Okay. So now this is. So now when we talk about the age of the sun as 10 billion years, it can survive for 10 billion years. All that equation that I showed in the beginning will have to be used for calculating that number 10 to the power of 10. Okay, so that is your physics, and you will learn it in your physics class, so I will not show the expression here. So you learn how to calculate that. That means you have a scheme of evolution that is taking place in the sky continuously. Okay, so now comes the question of how do we fix this hypothesis as correct? Theoretically, the equations are perfect, so you are happy. But then we have to show something in the sky that this is the case. So here you have a massive star. Okay, I think I'll skip all this because it's only repeating whatever I said till now. So what is a measure of age? Okay, here it gives a nice picture so you can enjoy this. So here you have the different types of stars, and based on the different types of stars, can you say one is older, one is younger? Both are looking alike. Okay, so which is young, which is old? How will you declare that? That is the question now. So the answer to that, this is the laboratory we have. This laboratory is like a sample. You go to a forest and then you will see a lot of deers there. Okay, so many of them going. So you want to understand the life cycle of that. So you will see a baby, you will see an old one, and you have features with which you will identify that this is a baby, this is an older one. This is the one which is going to be dead in a few months or something. All this you will be able to guess looking at the features. So here is such a group of stars which is called the open cluster. You can see such clusters with your eye. Kritika is the best example. If you can see Kritika, then that is the one which has these kinds of stars. Now you see the colors. The colors are the indicators of the temperature as well as the possible sequence of evolution. Okay. And they come in two varieties. This is called an open cluster. It is like a flower which has just opened. So it is called an open cluster. but physically it means that it is in a particular phase of evolution. Okay. So there are about 100 to 1000 stars, and the extent of this cluster is about 10 light years, 20 light years, and so on. And what we do, this has a name. This is called Jewel Box Cluster. The beautiful photographs you can get from the Hubble Space Telescope of this Jewel Box Cluster. And here is the color photos, and the colors are not realistic, but they have been made to look like this so that you get an idea of the difference in temperature and luminosity. These are the only two things with which you will have to prove that this is a young cluster or this is an old cluster. So let's see how we do it. So there are supergiants, and there are blue stars, there are red stars, and so on. Okay, and there is the word H alpha. I suppose you know what is H alpha. What is it? You see here H alpha. H alpha. What is H alpha? Louder. Somebody is whispering the answer. It's the Balmer line. You know what is the Balmer line? Okay, that's the Balmer. They are showing very strong Balmer lines, and Balmer lines are the ones which are visible in the. What's the color of this line? Have you seen a spectrum? Hydrogen spectrum? Okay, you see one and find out the color. Okay, so this is something which will wake you up from the sleep if you are sleeping already. So this is in the family, so you have many resemblances, okay, and then you look at the photograph and guess the age, right? So you have here, and then the clusters also we are going to make use of in the same way, but let's see what is the basic difference. We have an entire family photo, okay, and then you will estimate the ages. That's easy, all of you can do it. So you have the ages. The ages are all decided, and then what is the assumption that has gone into it? There is a trouble with this. In a human family, people are born at different times. Okay. Whereas, in the case of this cluster, they are all born together. They were all born at the same time, but then they evolved differently, and so one dies faster, one ages faster. That's the basic difference. Okay. So the assumption is that life expectancy is about 80 years. So you guess looking at the face and put the age there. Okay. But a cluster is a stellar family, but the stars do the reverse. What is it? They are born at the same time, but when they grow, one is large, one is massive, one is less massive, and so on. So, what is, okay, here the example given is 1642. What is special about 1642? You relate 1642 to something? Year. Birth year of Isaac Newton. That's why it is being chosen. Okay. The bigger, the faster. So, the one at the end, which is the largest, will evolve faster. Okay. So, how long will it live? That fellow will live only for 3 million years, and the next one will live only for 500 million years, and this one will live for 3000 million years, this one for 15,000 million years, and this one, because it's a very small star, it will live for a very long time. So, the family picture that I showed of the human cannot be applied here. That's the basic point I am trying to make you understand. They age at very different rates, the bigger, the faster. So here is Pleiades Kritika. This is how it looks through a large telescope. With the naked eye, you can make out the cluster beautifully. So let us study this cluster, and that diagram which I showed. So we will pick up individual stars from there and create a graph of that nature which showed what is the main sequence, when they are in the main sequence, whether they are all away from the main sequence, and so on. So that is the exercise that is done. So that is the main. So here you have the same graph, temperature increasing this way, luminosity. So we pick up star one by one, measure their luminosities using the telescope and create this graph. So that line is theoretical one, and you notice that something is strange here. You can see that it is not overlapping in the last top portion, it is not overlapping. So what is happening there? That is the clue. Okay. So different stars age differently, but in this graph we are seeing that they are all, according to the theory, at 0 age only. So most of them are young, but some show that they are not so young. And they are young in the meaning of years, but then they have evolved. So that's the graph, that's the indication from the graph. So that's the graph. So you can say that protostars and small stars are here, and the middle-sized stars are there. But what about the massive stars? They have already left the main sequence. They have evolved faster. So this is what our theory said. So we are proving it here. So this is how the cluster becomes a laboratory in the sky. Okay. When you use the word age here, it means how long ago all of them were formed. It's not that one was formed, one is younger, one is older, or something like that. Okay. And so here are some examples from the galactic center. So galactic center is in the direction of Sagittarius. There are so many young clusters there, with the help of which you can do this graph. This is the thing you can do. You can plot the graph, find out how long ago that particular cluster was formed. This region is rich with the cluster. See, that is M7, and here you have another one, and then you have so many images there. So this region of Sagittarius is very rich with so many nebulosities, clusters, and so on. So see, these are all the ones. There are so many. There is some dark material also, not dark matter, but dark material, which is hiding the light. So maybe there are more star forming regions there. So this is the laboratory. So now the questions are, why open clusters are all blue? Globular cluster, in the previous one, that is a M7 is a globular cluster. M7. You can see that it is not blue. Pleiades was blue in color. And why you see them only in some specific directions? You don't see them everywhere in the sky, only in some selected portions only you see. And why there are so many nebulae near the constellation of Sagittarius? Now all these questions will come to you when I show them, and you will seek answers and you will get very interesting results. Okay, but these clusters hide many more secrets. So there, I only told you one part of it, that there are laboratories in the sky. So this is the beehive, and the other is the globular cluster. This is a globular cluster, so you can make out the difference. The very shape itself, it looks like a globe, and there maybe 10,000 stars are contained in that small angle. Whereas here it is only about 1,000 stars. So that is also another interesting thing. So this is some kind of overlapping. There are some properties which is common for both the types of clusters. There are some which are different, and that study will give you very interesting results. Okay. I think I have convinced you that they are the laboratories. But then there is another small interesting thing that I want to say before concluding. So we think that the stars are stationary, but they do move. There is an apparent motion. Okay. So you have an example of a star called Barnard star, which is the fastest moving. Can you make out which is the star which has moved here? These are two photographs taken apart some few years. You can make out. Okay, I think there is an arrow. Can you see the blue arrow? You see the corresponding star here. So within a few years, the star has moved. So this is the kind of motion that you see in the sky. Now with this motion also, you can do a lot of things. For example, you can show that the sun is going around the center of the galaxy. Only these kinds of motions of the stars will reveal you that secret. But if you apply that to this cluster, it should not show anything because we just now told that they were all bound together in the same region of the sky and they are held together and therefore there should be no motion. But if you do this study to the individual clusters, you will get very interesting results. So you see a star may be moving like this, but when you are seeing from this direction, you see the projection of this motion in this plane, only in this plane. So that is the motion that I showed in the picture. But it can be moving in this direction also, in the radial direction. That you will get from the Doppler effect. So you have to combine the two components and get the sum, so that you will really know whether the star is going this way, or this way, or that way, which way it is going. So this kind of an exercise is being done by this satellite called Hipparcos, and it measures all these minute quantities and provides you the information on the movement of individual stars in the sky, accurate to milli-arc second. 1 arc second is 1 by 3600th of a degree. 1 milli-arc second is 1000th of that. So it can give you to that accuracy. So we will do this. I will just show one example for okay. Now let us say that we have 6 stars in surrounding the sun this way, and each of them appears to be moving randomly as we measure. But in reality, it's the sun which is moving in one direction, and therefore it appears to us that they are moving in different directions. So what you are going to do is the star streaming, how it will be. So because the sun is moving like this, all the stars should be moving in the opposite direction. But they have their own space velocity. So it will be a net effect of the two, and therefore you measure the radial velocity, you measure the transverse velocity which is in the plane, and then you get the, now you see the actual motion. The star appears, those red arrows are the ones which show the actual motion as you measure. So your motion, that is the motion of the solar system, is hidden in this. So you measure the motion of the individual star and then find out what is the velocity of the sun. And why is the sun having this velocity? Because it is going around the center of the galaxy. Now we will do the same thing for the cluster. Okay. Okay, that is how it appears. It appears as though stars are all moving in random directions, but then there is some order. Okay, I don't need this. Okay, here comes the example of the cluster called Hyades. Hyades is where it's in the constellation of Taurus, and that bright star is Rohini. Rohini is the star. So we do this measurement and find, and then plot. See, this is the interesting plot that you get. And Aldebaran or Rohini is, can you see, Aldebaran is marked there. all the stars appear to be moving in one specific direction, and they all seem to merge to a point there, whereas Rohini is moving in an opposite direction. Therefore, Rohini is not a member of this cluster. Although when you see in the sky only in the same direction, it is something which is much closer to us than the rest of the stars in the cluster. Now, this is the same thing which you get if you combine all the results from this Hipparchus catalog. So you can make out that all the stars of the clusters are having one velocity which leads to a point somewhere in the sky. So they were formed somewhere here, and gradually they have moved and come and occupied this region where we are seeing it today. So why did they all go and start there? So what is there? What is that point which is special? So that we have to find out. We have to do this exercise for all the clusters. Obviously, this will also tell you about the age, how long ago they were formed. So you already have estimated the age by the HR diagram, whether the two tally. So that is something which you can verify yourself. Okay, so this is something which I wanted to tell you, that all the theory that is told about the star formation and evolution is not from Chandamama, but it is basically from physics. And you have a method to verify them and you can do it. So I think I have convinced you. This is another interesting work done by Bade. He looked at one galaxy in the constellation of Andromeda, and then he did a very simple trick. He looked at this region first with a red filter and then with a blue filter. Okay, so when he did with red filter, it looked different. Okay, nothing, unresolved. There were no stars that were resolved. Then he repeated it with the red filter. Now you are seeing some stars. That means these are the stars where possibly star formation has taken place recently. So based on this, he classified the stars into population 1 and population 2. So this is another interesting observation that you can do. If you have access to telescope, you just take two images into different filters and you can pinpoint and say these are the young stars, these are the old stars, these are the star forming regions, and these are places where there is no star formation taking place. But all such answers will lead to further questions. So this is the typical globular cluster. Now, can you resolve this? Even the largest telescope will, you will find it extremely difficult to pinpoint every star, get its spectrum, get its proper motion, get its radial velocity, and so on. So how do we work with such clusters? So that is the question that is coming up. You think about the answers for them. Okay, so this is where I stop. I have told you there are laboratories in the sky. So I think you believe me now that they are the laboratories in the sky. Now it is for you to go and work in this lab. So how will you do it? Please think about it and start working on that. Okay. If you have any questions, I will answer. I don't know how much time I have taken. Have I exceeded or cut into your lunch hour? I hope today some more questions will come.
Good afternoon, ma'am. My question is, you mentioned that high temperatures cannot be possibly made on Earth. It cannot be incorporated into gravity. But in China, they have done this thing called artificial sun. And they also aim to have temperature, to have loaded temperature 10 times more than the sun. So,
Okay. Yes. What's your question?
So, what is the timing of that?
Okay. That machine is called a tokamak. Tokamak is there in India. There are two of them. You don't have to go to China. So please go to Gandhinagar, which is very close to Ahmedabad. There is an institute of plasma research there, and they have a tokamak. And with all that huge facility, they call it a flash. The energy is available for a fraction of a second. That's all. For that, they will work for 10 years, 12 years. Okay. And there is a similar one in Saha Institute of Nuclear Physics in Calcutta. So please, your physics students, you should go there and see that setup. Such a huge, massive setup for a fraction of a second. So don't have to go to China or wait for China to boast about it. Our Indians have done it. Okay.
Uh, I have a question.
You have, huh?
Yes. Uh, the results of the findings of the latest space telescope,
JWS.
James Webb,
Hmm.
the news say that they seriously contradict the picture of the expanding universe that we have formed on the basis of the standard.
I did not go to that laboratory.
Yeah.
I am in a different laboratory now.
So how do you interpret all these findings?
No, see, we had a theory of stellar evolution 100 years ago. And subsequently, we were believing that the neutron star concept is wrong and it's only for a theory and there is no practical application of that. And so people believe that every star will have to be undergoing that within that Chandrasekhar mass limit and so on. Till the first neutron star was discovered. Then the entire theory changed, all the stellar evolution theory changed. Similarly, now we are in for a change. As you improve your vision.
But that appears to lead to a cataclysmic change.
Of course, yes. But these timescales are so vast that there is no way to verify them unless you look back in time with accuracy. So how fast you can do that, how good you can do that will be deciding whether what you predicted is correct or not. That's where JWST will come into picture. Okay, how far you can go back in time. So whether the stars formed first or whether the galaxies formed first, whether there was an inflation at all these things can be verified only at that stage, isn't it? We have to wait, that's all. Unless there are theories coming, and then what was written in textbook 25 years ago, now we have to remove and replace them with newer ideas. That's the process of learning. So we have to wait for new results.
Dr. I have two questions. First question is you said stars were all born at the same time and only they were born at different times. But in another side you said we could observe newly forming stars, star cluster.
The stars are forming even today. So for every galaxy, they fix what is called as the star formation rate. That means every year, how much of mass of the galaxy is converted into stars. That is happening even today. Therefore, stars are born continuously, and at the same time, the stars are we are seeing supernovae. That means they are dead also. So it's a continuous cycle. What happens to the dead star? If it is a neutron star, we won't see the star, but it is lying somewhere. It doesn't emit any light. We don't know whether it exists or not, unless it has a companion which is going around it. But what happened to the material? 90% of the mass which it had owned as a star is now back for the interstellar medium to form fresh generation of stars. So it's a continuous process that is happening. So when you say star forming region, you are looking at a freshly born star. When you are looking at a nebula, the nebula can be because of the depth of the star. So you have examples of both in the sky.
The second question is in the graph of luminosity and temperature, we could observe the theoretical kind. It's based on this equation.
No, not one equation.
I'm asking which equation.
No, the theory has been developed by so many people over so many decades. One of the first in that is again Chandrasekhar. Okay, so it was Eddington, Hans Bethe, all these people who talked about the production of energy. Then how the energy from the core gets transmitted to the photosphere. Photosphere is that region. It's a gaseous body. So where do you put the boundary? The boundary is decided by that point from where light can escape. That is photosphere. So how is the energy transmitted? Is it convection or radiation? So these kinds of processes which help the energy to come out, they were all calculated by Chandrasekhar. Radiative transfer techniques and all those. So you have a set of equations there. And after they have reached that, then there is a convection current taking place, and there are so many people who have worked on that theory. And finally, somebody else, one who will sit and make a model of if so much of helium is there, if so much of magnesium is there, what is the kind of emission you expect? If so much of silicon also is there in the photospheric region, what is it that you expect? Now, all these theoretical models are worked out by various people, Mihala, Skurk, so many names come there. It's not one individual, so I cannot give you one equation. Okay.
My question is why is the graph been
A very good question. I thought you knew about it. Anyway, now that you have asked the question, it's very good because my assumption was wrong. HR corresponds to two people. H is Herström, R is Russell. It so happened that they were living in different parts. One was in Europe and the other was in America. And they both somehow decided that we have now observed so many stars, we have got their intrinsic magnitude, we have got their temperature. Let's see how they are distributed. They plotted it. And they were not, it was an independent result that they got. So to honor both of them, it is called a HR diagram, Hertzsprung-Russell diagram. Both are great scientists. If you can see any book on astronomy, their bio sketches will be given. And that diagram you use for every aspect, for the formation of the star, for the determination of the age of the star, or for studying the colors of the star, or even for applying Saha's ionization equation. For everything you use the diagram. So it's a standard diagram, so it is used everywhere. HR is Hertzsprung and Russell, two people. Okay, if there are no questions, I think the others have understood. I thank you for this opportunity, the Department of Physics and the Cosmos. So I'm happy that at least some questions came up, and please develop this habit of asking questions without hesitating what others will think about you. Because she asked one about 1HR. All of you came to know that what is H and R. You all have to thank her because she asked that question. So similarly, others also should ask questions and get it clarified so that the person standing on this side, whether it's me or somebody else, will not take it for granted that you know everything. Okay? Please feel free to ask questions that you develop that habit. Thank you. Thank you, Amrita.
So, before concluding it, I say that ma'am has written many books in Kannada and also in English. And I think if you can get those books and are reading it, you will get more ideas. And,
we are bringing out one encyclopedia also, which will be ready in another month. It's about 450 pages in Kannada. Professor Prasad also has contributed on the same topic on which he asked the question. Okay, so have some kind of an overview of all about astronomy, starting from naked eye astronomy right up to infrared astronomy and cosmology. So that may be a good starting point for you if you want to start reading in Kannada. Otherwise, English you have ample books. There is no problem. I have written other books also in Kannada, and there was this Professor G.K. Narayan Rao, who was in Mysuru and who has written many books in Kannada on astronomy. So please develop that habit of reading. Come out of the reading from internet. Read hard copy books. Okay. Okay. Thanks.
Yeah, on that note, I would like to thank Dr. Shylaja for coming here from Bengaluru to give a lecture to me. On behalf of the Department of Studies in Physics and the Cosmology Education and Research Training Center, I thank you.
Thank you.
Great thanks to you for coming here and doing this talk. I hope you have a nice time and that session. I can follow on one email if you have some doubts.
I had written my email right in the beginning.
Oh, so yeah, if you have any doubts and query, you can email one or come to us in return for
Okay, thanks.
thank you very much.
Thank you.